Hello everyone, my name is Sunil Mishra. Welcome to this course on artificial neural network. This course is going to be primarily about deep learning, and the course is structured in a series of video lectures. We are going to talk about fundamentals of deep learning, the background behind it, how it all came into existence. This is not a new course, this is not a new topic, this has been there since quite some time, so we'll talk about that. Then we'll try to talk about some of the building blocks of deep learning neural networks. And in the next lecture, we'll try to create a model. Then we'll try to tune the model using a typical ANN model. Then we'll talk about convolutional network, which is typically used in image processing or videography and things like that. Then we'll talk about recurrent neural network, which is very commonly used these days in speech processing and other language processing. And then eventually we'll talk about the word-to-vec or word processing, which is like representation of language in the mathematical model, in the deep learning model. And essentially we'll cover this through a series of video lectures. I hope you will find them interesting. I have tried to make them non-technical, so even if you do not have a background in any of these, even if you do not have a technical background, you would be able to appreciate and understand this topic. The idea is to know the possibilities that can be explored using deep learning and neural network. I hope you find it useful, and I hope to see you in the next lecture. Thank you. Welcome to this first lecture on deep learning. Here we are going to talk about the inspiration behind deep learning, and as I said that this is not a new topic, this has been there in existence for quite some time. But in this lecture what we'll do is that we'll go behind the inspiration, which is like the biological neuron. So we'll talk a bit about biological neuron and then how the biological neuron was the idea behind artificial neuron, and then we'll try to construct a network. So to talk about the biological neuron, the first thing that comes to the picture is reticular theory. When first time people tried to understand human brain, they thought human brain was different from the rest of the body cells, and what they believed is that human brain is a set of connected networked cell, unlike the other cells in the body that are discrete. So this was known as reticular theory, and this was as old as 1871-73, and this was proposed by a gentleman called Joseph von Gerlach. Okay. Later on, Camillo Golgi, he used a staining technique to figure out how the cells in the brain are organized. And then he drew a picture of the brain cells. That time they were not known as neuron because the term neuron itself was not coined. And after the staining, he came to the same conclusion as reticular theory. So he said the same thing, that brain cells are not discrete cells, but they are continuous network of organism, unlike other parts of the body. Coming to the next phase, sometime in 1888, Santiago Ramon Cajal, and this is a very famous picture drawn by him of the brain cells. So he used the same technique that was used previously, but he came to a completely different conclusion. And the conclusion was that like the other cells in the body, the brain cells are also distinct. They have like discrete cells that are interconnected. And this theory was later on proposed as neuron doctrine. And that was a time around which all the terms like proton, neutron, all those things were being devised. So neuron was in the same philosophy, right? So this is where this modern concept of neuron came into being. And in 1906, but this debate was still not settled whether human brain is one giant network or it is a collection of cells. So in 1906, when Nobel Prize for Medicine was given, both of them, Golgi and Cajal, both of them were jointly awarded the award. So the point is that even till then, it was not conclusively proven which is the structure of the brain. It was finally settled in 1950 with the invention of electron microscope, and then it was observed that there is a small gap between two brain cells, and that is known as synapses. And today we know that yes, the brain cells are discrete cells, they are interconnected, they are networked, and this is where we come to the current understanding of neurons. Okay, so this is a picture depicting what we know of neuron today. The reason I'm going about this description of neuron is because this has been the inspiration of development of artificial neuron, and a lot of concepts of the biological neuron have been implemented in what we call ANN or CNN. Right, so this is how a neuron is there in our brain, right? So it has different parts. The first part, the topmost part, what you see more like a tree kind of structure, is called dendrite. So this is where the neuron get the signal from other neuron, and typically one neuron may have thousands of these dendrites. So these are like input connections, right? So once you get the input from different neuron, then these inputs are aggregated at the cell body, what is called soma. So this is just like arithmetic sum of all the electrical signal that a neuron gets. And then based on the summation, the neuron decides whether it has to fire or it should not fire. And that is based on a property called action potential. So if the action potential of the neuron is more than the threshold, then the neuron fires, and if it is less, then the neuron doesn't fire. The meaning of firing of neuron is that this neuron transmits the electrical signal from its body to the tail, what is called axon terminal. So if the neuron decides to fire, then the electrical signal passes through the body, and what you see is called axon. This is covered by a myelin sheet in case they are long neurons, and finally it reaches the end of the neuron, which is called a synapsis. So this is a place where this particular neuron is connected with some other neuron, and they transmit the electrical signal using what we call neurotransmitters. So now these are specific biological term, and we will not go too much into detail. The point here that I'm trying to make is that these are individual cells that are connected to each other, and there is a signal processing system that happens in our brain. So there are close to 100 billion neurons in an adult, and each neuron, as I said, has up to 10,000 connections using dendrites. Right, so you can well imagine that how complex this structure is, and it will have trillions of structure or connections within our brain. Each of these neurons may vary in size. Some of them are very tiny, and some of them actually go beyond a meter as well. Okay, the mechanism of transmission is all through electrical signals, and as we saw previously, these electrical signals pass from the soma to the axon body and to the axon terminals. And there are some principles behind how these neurons are organized. One of them is very commonly known in neuroscience as neurons that fire together, wire together. So this is how all our learning and everything happens. And the other principle is that if you do not use a connection, then you lose it. Right? So this was a bit of background on how the biological neuron works. And then we'll see how this concept is useful when we try to construct an artificial neuron. Okay, so here we come to the artificial neuron. The first such neuron was postulated by McAloon-Pitts neuron, which is very commonly known as MP neuron. Right, so here again, just as a biological neuron, you can segregate that in different layers. What you see, X1, X2, X3, X4, these are the input layers. Then you see another aggregation layer, what we call is a function which just sums up all the inputs. Okay, so this is the input layer. Then you see aggregation layer, which is like the, if you remember the neuron that we described, it is like the soma or the cell body. Then there is a decision layer. So this is a part where the neuron decides whether it has to fire or it should not fire. and finally the output layer. So this is how the MP neuron was constructed in the initial phase. In fact, this was a very simplistic model. So he presumed that all the inputs are Boolean inputs. So the value they can assume is only 0 or 1, and they are summed up at function f. And if the value is more than certain threshold, then the output is yes or no. Right. So this is how we can depict that mathematically. So assume that all the inputs and outputs are 0 or 1. So let's say y equal to 1 if the sum of all the inputs is more than a threshold value, and if that value is less than the threshold, then it doesn't fire. So this is how McClellan-Pitts neuron was constructed. And actually using this neuron, you can create most of the logic gates. So and or not gates can be created using a combination of these McClellan-Pitts neuron. But not all gates can be created. For example, XOR gate cannot be created, and that was one of the limitation of this particular neuron. Okay. Next phase of evolution was perceptron. Okay. Now the difference between MP neuron and perceptron is primarily, there are actually two differences. One is all the inputs are not Boolean, but they could be real values, real numbers. And as we know that in real life, all the inputs could be real numbers. For example, if you have to decide whether you want to go for a movie or not, there could be a lot of inputs for that, right? So for example, there could be something like who is the actor, what is the genre of the movie, what is the rating of the movie. So some of these are Boolean values, some of these are real numbers, and so these inputs could be different. So that was one change in the perceptron model. Second change that was brought in was the weights, right? So you see different W1, W2, W3, W4, W5. These are the weights that are assigned to each of the input. And we can actually correlate that in our real life also, right? So sometimes, for example, the actor could be more important to decide about the movie, or the genre could be more important. So the model that was created had the ability to learn these weights based on the real life scenario. So these are the basic difference. And again, using this, you can create all the logic gates. But even perceptron model was not able to solve the XOR gate, right? And then it resulted into a lot of criticism of this model. And then, in fact, a lot of people said that perceptron probably cannot solve most of the real life problem. And then that was a time when funding in AI project dwindled. And in fact, this happened many times in the history. And but this is the point when funding actually majorly reduced, and then this resulted in what we call AI winter. So after this time, a lot of universities and a lot of governments who were funding for the AI project, they stopped funding because they believed that perceptron could not solve wide variety of the real life problem. Okay, now a little bit more about the perceptron, how it is created, right? So we saw different inputs. So in this case, I'm just taking one particular input, like let's say critics rating, and it's a linear model. So linear model is represented as Z equal to W into X plus B. B is known as the bias and W is known as the weight. And the process of learning is actually learning the value of the weight as well as the biases. And this is also represented as a step function. So you can see that if the value is less than certain threshold, then the value is 0, otherwise the value is 1. But here the problem with this function is that it is a sharp decline. So it is a steep decline. If the value is less than certain threshold, the output is 0. If it is more, the output is 1. But this is not how the real life decisions are made. I mean, there is very little difference between 0.49 and 0.51, but this function actually just make it either yes or no. But in real life, these are very close decision. Okay, so this is where this sigmoid neuron comes into picture. It is actually a logistic function, and this is like a standard logistic function. If we know y is equal to 1 by 1 plus epsilon to the power wi and xi. And what this does is that it actually smoothens the output function. So earlier these output function had a sharp decline. Now this is a smooth S curve, right? So this function becomes differentiable, and there's an advantage of a function being differentiable because we'll see that because the slope determines how do you learn the weights and the biases, right? The other advantage is that this brings the output value between 0 and 1. So this actually makes it more manageable because we also know probability also has a similar property of having value between 0 to 1. So it is more useful, and in real life most of the times we use sigmoid function. Okay, so finally come to the multi-layered perceptron, right? So multi-layered perceptron, or what we call is advent of deep learning, is where we have hidden layer in between input layer and output layer, and there could be n number of hidden layers, right? And these hidden layers actually are the abstract property that are arrived at based on the combination of input and the weights. And there is a theorem that has come up that time known as universal approximation theorem, which is a very popular theorem. And this restarted the investment in AI. And this theorem says that a simple multi-layered network of neutrons with a single hidden layer can approximate any continuous function to any desired level of approximation. Okay. Now what this means is that a single neural network with even one layer of one hidden layer can solve any kind of real life problem if it has a continuous function. So any continuous function can be solved through that, right? So this brought back the faith in neural network and deep learning for that matter, and then the investment and everything started all over again. So this is a bit about historical development, how AI research and deep learning has progressed over the time. And as I said, this is very old. So this started as early as 1950s from MP neuron, and then there were some breaks in between. So there was an AI winter in 1969-86. Then different things started, and these are some of the milestones that we talk about when we talk of deep learning. 1950, Alan Turing, I think this is one of the most famous tests that even today is applicable. What we call is Turing test, and this is a simple test that requires a machine to carry on a conversation via text with a human being, and after 5 minutes the human is convinced that the other person is a human being, then the machine is said to have passed the Turing test. Okay. Then there are other significant milestones like the recognition of handwritten digits that was done in 1989. Then of course other milestones in the gaming. So 1997, IBM has beaten Chessmaster. Then there was ImageNet challenge. So there were a series of ImageNet challenges that were open to everybody, and that contributed to the development of the convolutional neural network. Then there are other milestones like deepface from Facebook, face recognition algorithm that actually has a better accuracy than the human face recognition. Then AlphaGo was important because it actually learned by itself. So instead of predefined rule, using machine learning and deep learning, it created its own learning algorithm. Okay. Now briefly about the application of deep learning in the real life. So there are two broad applications. One is in the area of automation. So automation is typically like whatever work a human can do, machine can do it better, faster, and things like that, right? So this is where something like image recognition even humans can do, but probably machines can do faster. So automating the work that human was doing, and all these like image captioning, language modeling, machine translation, fraud detection, document classification, all these are examples of automation. The second broad category is creativity, like where probably it is trying to even beat human in various areas. So this is something which is not already predefined, but this is something that deep learning networks are trying to generate something which has not existed before, and something like using now neural network, you can create new images, you can create some videos, you can create some art, you can mix three different art pictures, and you can make, in fact in some cases they have also published automated news articles and poetry and things like that. So these are the areas of creativity. So this is what I broadly wanted to speak about on the background of deep neural network, and this is like, broad applications where all it is being used. Now next lecture onward we'll start going into details of the deep learning and neural network, how to construct that, and I hope you will find that useful. See you in the next lecture. Thank you. Hello everyone, and welcome to the second session on deep learning. In the previous session, we spoke about the inspiration behind neural network and the history behind it. In this session, we are going to talk about the high-level concepts and what makes up this field. So these are broad things that we're going to talk about in this session. One is the evolution of deep learning from machine learning. Then we'll try to construct a neural network, and we'll try to understand what are the key concepts using which we solve a model, and gradient descent is one of them. Then we'll talk about back propagation, and then we'll take an example of classification problems. So regression and classification, they are handled differently in neural network. So in this particular section, we'll cover that. Okay, so the regression problem has not been is not a new topic. It's been there. So in this particular example, we try to calculate the price of a house based on the area, right? So we all know that the price of the house can depend on the area of the house, and we are trying to figure out what is the relationship between that, right? So there are independent variables and dependent variables. So in this particular example, there is just a graphical representation of these two variables, and then the model is trying to predict what is the price, what will be the price of the house given the area, right? So we presume that there is a linear relationship. So this model can be expressed as P is equal to W, which is a weight, plus bias. Right, so this is how typically a machine learning or regression problem is constructed. Okay, so what do we do as part of solving? We try to fit a line through these dots so that the variability of the individual data points from the predicted value is minimum, and that's why this term mean square error comes into picture. So what mean square error does is it tries to find out the deviation. I mean, if we talk mathematically, is the perpendicular distance of the data point from the line, right? And the reason we take square is that if we just take an arithmetic value, then the positive and negative will cancel out each other. So even if the data points are widely separated, we may get an impression that the line is representing the distribution. So when we square the error, then the positive and negative cancel out each other, and actually they do not cancel out each other. So we get the true picture of the error. So mean square error is going to be the common factor for regression analysis, and we use that in neural network also, right? And some terminology. So W is known as the weight here, and B is known as the bias. And typically, if there is a linear function, then definitely this model can solve the problem, right? There is no need of hidden neuron, but as we know in real life, the relationships are not linear. The independent and dependent variables are not linearly correlated, and that's why we have a need to have a hidden representation, or what we call as polynomial representation, right? So that's where neural network comes into picture. That's where ANN and deep learning has its presence. Okay, so here we'll try to construct a basic deep neural network, and we'll try to understand what are the different components of that, right? So we try to read this network from below. What you see at the bottommost are the input layers. So we can take the same example as the area and the price, and in this case we presume that there is no linear relationship. Rather, there is a kind of a polynomial relationship or hidden relationship that we do not understand. So that's where this neural network can be used to solve that problem, right? So the first layer is what we call as a data layer, right? Then we try to create multiple hidden layers in between the input and the output layer. So here y1, y2 are the output layers, and then there are 3 layers of hidden neurons, right? So each neuron again has each hidden neuron has 2 parts. One is the aggregation layer, and then second is the activation layer, just that we saw in the example of a biological neuron, right? So W1, for example, it's a matrix representation of weight, and you can see all the inputs are, in this particular case, all the inputs are connected to all the hidden neurons, while that may not be the case in real life. Okay, so we have seen data. Then second is a model. So model is what is represented here as a function of the input variable to the output variable, and each of the hidden neuron layer can be represented as a step function. So in this particular example, you can see y, which is a function of x, can be represented as different functions of the weight and biases of each of the neurons. So we can move in steps and then we can reach the output. So that's how the model is constructed. Okay, what we do as part of machine learning is that when we feed it data and input and output are arrived at, error is determined, then weight and biases are actually evaluated. The algorithm or the network learns weight and biases to minimize the prediction error. So that is the whole purpose of deep learning, and that's where it differs from other prediction method, because here the networks evolve. Networks learn the parameters to correctly predict the output value. So there is something to learn. Okay, and then the algorithm. So there could be different types of algorithm. We saw in the previous example of price versus the area, and typical for numerical algorithms, we use gradient descent, and there are other methods also that we'll see later. Okay, and eventually we try to solve what is typically called cost function or objective function, and the objective of the algorithm is to minimize the objective function, the cost function. So in the previous example, the objective was to minimize the predicted price of the house versus the actual price of the house, and this is represented as mean square error. So these are the various components of typical deep neural network. Now when we try to solve some of these network using the modern tools like TensorFlow and all these layers you may not be exposed directly, and all these will be kind of built in, but this is what the fundamental principle behind different layers are. Okay, one of the key principle of solving a deep neural network is called gradient descent, right? So gradient descent, as an intuition, you can think of somebody rolling a ball down the valley. So what the ball will do? Ball will try to figure out the lowest point, right? So it will roll down the decline and it will reach the minimum point. And this minimum point is where what we call is the error is minimum, right? So, or what we call is a global optima. And so this is the point that the algorithm is trying to find. What is the point at which the overall expected error is the minimum? Now there are concepts like local optima and global optima, and there are again methodology to solve them. But this is the overall principle, that you try to find out the lowest point in the error surface, and this is what typically an error surface will look like. So if you start at any point in the error surface and you move towards a direction where the error is minimized, then eventually you reach a point where you reach the minimum value, and that is what when we say that the network has found out the optimum value. And then there are algorithms to move in certain directions. So going with the principle of calculus, what we do is that at any point in time we find out the gradient of that point with respect to the error surface, and the movement is done in opposite to the gradient direction, right? So here you see, for example, weight and biases, and T and T plus 1 are the update steps. So at each update step, like WT plus 1, you take the position at the previous step, and then you actually find out a difference of the differential and multiply that with a small constant, what is called as learning rate, and then you arrive at the new point. So that's how you keep moving in the direction of the global optimum or minimum value. So this is a key principle of gradient descent. I mean, fundamental for solving any neural network. Okay, then there are different types of gradient descent, right? So one of them is called momentum based gradient descent. The simple intuition behind this is that if you're moving fast, if you're actually on a flat surface, then you should be moving fast. If you're on a very steep decline, then you should be moving slow, right? So the update values are accordingly adjusted, and this makes sense, right? So for example, if you're in a plateau, then to reach the minimum point of the valley, you have to move faster on the plateau. At the same time, if you're, let's say, on the side of the hill, then you have to move slowly to reach the global minimum, right? So this is a principle of based on the momentum you change your update rule. Okay. The second rule is called Nesterov gradient descent. In this case, the change from the previous rule is that instead of finding the gradient at the current point, the algorithm tries to find out the gradient at the next update point. And then if there is a change in the direction, change in the gradient, then the algorithm presumes that it should go back to the previous point and then update it again. So this is used typically to reduce the U-turn, right? So basically what you're doing when you're doing momentum based gradient descent and you're updating the gradient, then you may overshoot the optimum or the minimum value, and then you have to come back, right? Because when you see the direction of the gradient has changed. So what this particular algorithm does is that before updating the weight or the bias, it moves the value one step ahead and then sees if the direction of the gradient has changed. Okay, so this minimizes the U-turn. These are actually optimization techniques using which algorithm can find out the minima quickly. Then there is another method called RMS prop. This is typically used if there are multiple variables and not all of them are getting updated equally. there could be some sparse data, there could be some dense data. So this particular algorithm takes care of sparse data not getting updated enough. And then one of the most common technique used is ADAM, adaptive momentum gradient, and this is what typically is used in many of the algorithms today. Now the point that is being made here is that the gradient update formula is not uniform, and based on the context and situation, it can be updated in different way. But the overall objective is to find out the or to minimize the cost function, and how quickly we can reach the minimum value, because learning has a cost, right? So every time you update, there is a compute cost involved, there is a learning cost involved, and all this algorithm actually tries to make sure that your program reaches the global minimum at the least number of iterations. Okay. Now, one of the key principles of this neural network has been backpropagation. And backpropagation works again on a very simple principle. Okay, so for example, using the previous algorithm, you tried to find out the weight and biases, and then you eventually found one output, right? Now that output will have some variation from the actual value. So this is there will be error of that output. Now what backpropagation does is that it tries to reflect these errors all through the chain and updates the weights and biases. So for example, let's say in this particular case, the end value is, let's say the last node is output value y, and there is some variation in that, right? So what it will do, it will try to divide those variations into all the neurons it is connected in the next level. Okay, and the same thing will be replicated for the other layers. So for example, the neuron at the layer 2 will do the same thing for the neurons at the layer 3 till it reaches the input point. So actually it is traversing the network in the reverse way, so that the error is reflected correctly, and the neuron that is contributing to the error, they are adjusted well, right? So definitely this again uses the calculus formula to find out the gradient and then kind of update the value of weight and biases. Backpropagation had been very fundamental for the development of neural network, and this has actually led into the advancement of this field, I'll say. Okay, now here previously we saw a regression problem, example where the variables are linearly, or maybe they are real numbers that they are covariant. In this particular case, we have taken a distribution example, right? So for example, there is a bag, and in the bag there are balls of different colors. So there are some balls with red color, blue and green, right? And there is an actual distribution. So distribution is in this particular case, for example, is 25, 35, 40. So there are, for example, 100 balls, right? So this is the actual distribution. Now, one of the problem of deep neural network or any algorithm is to find out the probability of the balls based on some random sampling, right? So for example, the algorithm predicts something like 10, 25, 65. So there is a variation between the actual distribution and the predicted distribution. Now, what is the best way to study this difference? Of course, one way is the mean square error that we have seen earlier. So we can find out what is the difference between, for example, predicted red percentage ball and predicted an actual red percentage ball, and then like that we sum up all the values and find out the minimum value. But in case of classification problem, there are a few uniqueness, right? So one of the uniqueness is that all these probabilities, they sum up to 1. So estimated probability as well as actual probability, both of them sum up to 1. Yeah. So there is a better way to represent the probability distribution problem, and that is known as cross entropy. And this is mathematically represented as probability distribution of probability I and P and Q are the predicted and actual distribution here. And what it does is that it tries to minimize the variance between the actual and the predicted value. This log is used to capture this variation in the most optimum way, right? So this is again used very commonly for classification problem. This is also known as softmax, and you will find that very commonly used for all things like image classification or any kind of classification for that matter. So cross entropy and mean square error, these are two important cost functions that are used in the deep neural network. Yeah, so these were the basic principles that I wanted to touch upon. I know these are not all, but these are some of the very fundamental tools that you will come across when you try to understand how a deep neural network works. So thank you and see you in the next session. Hello everyone. Welcome to this third session on deep neural network for beginners. In the previous session, we tried to construct a basic neural network. We saw different layers, how are the input and output are related, how the hidden neuron networks are created. In this particular session, we'll try to improve the neural network. One of the key component of deep learning is how do you fine-tune your network, how do you fine-tune the variables and the hyperparameters to obtain the most optimum result, right? So there are different techniques that are used for that, and these are techniques that we are trying to cover in this particular session. So we'll talk about what we call dimensionality reduction, then segregating data into train, validate and test. We'll talk about the model complexity, like how close your model should replicate the trained data. Then we'll talk about regularization, like one of the problem in deep learning is overfitting, and regularization is an attempt to solve that. And then we'll also try to cover the activation function. We saw activation function is actually, it helps you determine the output value, and choice of activation function is very important for finding out the right network. So starting with the dimensionality reduction. So one of the problem in real life is that as the number of independent variables increase, as the number of features increase, the complexity of the problem increases exponentially, right? So it becomes immensely difficult to solve a problem with multiple features, multiple independent variables. The learning cost and the cost of training increases a lot, right? So there are various methods. One of the basic method is you take out the non-significant features. So if there are, let's say, 10 independent variables, and you believe that, or you find out that half of them actually are not significantly affecting the output, then these can be just removed. So you try to figure out the most significant features. So that is one way of reducing dimension. But you can only do so much with this principle, because there could be dimensions that are mildly affecting, so you cannot completely get rid of them. So one of the method to reduce the dimension in such case is called principal component analysis, and it's not very difficult to understand that. The intuition behind this is that can we create new dimension which could be combination of existing dimensions, okay, but they reduce the number of dimensions overall, right? So in this example we'll try to do that. We can take the same example of price versus area of the house, and we have just plotted them in this diagram. So for example, you can take x is the area and y is the price of the house, and these are different house prices, right? So here we have represented the data in two bases, right? So x basis, and so these are called bases, x and y, and they are orthogonal in this case. They are 90 degrees. That's how the typical graphs are represented, right? Now if you see, I'll just go back to the previous diagram. So if you see, all these data points have high variability both across x and y. So the data points are changing in value both respect to x and y. Now what we are trying to do is that we are trying to find out new dimensions. Suppose we come up with a new dimension called u1 and u2, right, that are orthogonal just like the previous x and y. They are perpendicular to each other, but they are actually created in such a way that the variability along the line of u1 is very high, while variability along the line of u2 is very low, right? So this is again called orthogonal vector because both of them are perpendicular to each other. And so what we have done as a process of this is that we have come up with a dimension u1 along which we can clearly segregate the data. At the same time, we have come up with a dimension u2 along which there is no significant variation. So what this essentially says is that we can get rid of u2 dimension and the entire x and y data can be represented as u1. So this is what in nutshell principal component analysis does. It tries to come up with a new dimension which could be combination of existing dimensions along which the variance is very high and the covariance is very low, right? So by doing this we can bring down the number of features or number of the independent variables to a large extent, and this will help us in solving the making the problem practical or small enough to solve them. Okay, this is another way of doing this dimensionality reduction. So in this particular case, these are called autoencoders. So what we try to do is that we try to find out a hidden representation of the data which has lesser dimension than the input, right? So if you see, for example, there are 5 neurons or 5 input data, and they are actually represented in a smaller hidden layer, okay, which is shown here as H. And then so what it does is that it takes the input, encodes the input into this hidden layer, and then it can be decoded using that decoder layer. So it has 2 layers, encoder layer and decoder layer. So what it does as part of this is that the first function, it encodes the input into a smaller compact form, and then actually it decodes the output layer. So as part of this, what we try to do is that we try to minimize the error between the input and output. So if there is very little variation between input and output, then we can say the hidden layer is the correct representation of the input layer, of the input data. So by doing this, what we are doing is that we are trying to create a compact model of the real data or real business data in the real life, right? Now there could be different types of autoencoders. So some of them are called under complete or over complete. Under complete is where the hidden layers are smaller than the input layer, and over complete is where the hidden layers are bigger in size than the input layer. Now this goes contrary to what we have been saying, right? So here the dimension is increased, but we do use that in the deep neural network in some cases where there could be variables that are correlated with each other. For example, let's say the body mass index, right? So it could be it's a fraction of body and mass, right? So in this case, the hidden layer could be an over complete layer that could expand the body and mass as two independent variables rather than the ratio being just one independent variable. Okay. One of the principles to arrive at a better model is how do we handle the data, because neural network is all about learning from data. The better the data is represented, the better data is cleaned and how it is optimized, the better your model will be in predicting the real value. So some of the principles that the data scientist uses, they divide data into multiple fractions. So one of them is, the biggest fraction is typically the trained data. So this is the data using which you train your algorithm and you optimize. This is what the algorithm uses to learn the value of weights and biases and different layers in the network. Then once you train your network using this data, then you validate this using a smaller fraction of the validate data, right? So this is a data set used to tune the model. Again, all these are part of typically the same sample. What is generally done is that randomly you divide your data universe into three different categories, and then you use them to fine tune some of the parameters or hyperparameters. Okay, and the third part is the test data. This is the data that is used to evaluate your model, right? So train data is used to train the model, validate data is used to tune the hyperparameters of the model, and validate data is not used to learn the model. So weight and biases, which is typically part of the model, is not learned as part of validate. And test is finally when you test your errors. Right now, one of the problem in the neural network is known as overfitting. So, and we'll see that later how it happens. But if you train your data too much with the existing data set, what your data set will do, what your algorithm will do, is that it will minimize the error with the training data. So you will not find any variation within the training data, but the moment you take it to the test data, the variation will be very high. So what the algorithm has done is it has overfitted with the trained data. So it always gives zero error or very less error, while that may not be the real case. So there are techniques to overcome that, and then we'll see that how it is done. Okay, so one of the principle in the neural network is to find out the right model, the model that represents the data set in your training set, right? So here we have taken one example of, let's say there is a sinusoidal wave, that is the data set that is given, right? Now there are two ways to represent this data set. One could be a simple model. So a simple model is just a straight line depicted as y equal to mx plus c. So if you use a simple model, of course there will be little variation between the trained data and the test data. Okay, but if you look at this model actually is at a great variance with the true function. So this is what is called, if you take red is a true function and the blue line is your simple model, then then it has high bias. Bias means the difference between the actual value and the predicted value, the mean square error of that is very high. So this is not the good prediction. This is not the best prediction. While if we take a complex model, so in this case, let's say if we take a polynomial of 25 degree, okay, and we feed this training data, then what we'll do is that we'll try to create something like what we see in the green line, right? So what happens here is that there is high variation. So in this case, what will happen is there is low bias, right? So there is very little variation between the predicted value and the actual value, okay? But this will result into high variance between the trained data and the test data, okay? So there is always a trade-off between which model to select that will have low variance, at the same time low bias. You want your data or your model to be such that it has not only less error in the training data set, but it should also have less error in the test data set, right? So that is the whole selection methodology that works on, and that's why it is said that you should not drive the error in your training data set to 0, because in that case you will have high variance with the test data set, okay? So this is what is known as a problem of overfitting, and to solve that overfitting, what typically scientists use is called regularization, right? So regularization is done to overcome this problem of having 0 error in the training data set, but very high error in the test data set. Okay, now there are different methods to do this regularization. One of them is called weight decaying, where you do not allow the weights to assume any value. Okay, and now what happens is that if you give any algorithm some input value and the output value, and if you allow the weights to range from anything to anything, the weights will adjust in such a way that they will always correctly predict the output, right? But if we restrict the weights that they cannot assume any value, then some minimum error will always remain. And this is the idea of regularization, that don't drive the training error to 0. Okay, other way could be, we saw the example of autoencoders. So there were encoding weights and decoding weights. So one of the way to minimize or reduce overfitting is to tie these two weights. So all these two weights have to be the same. Another way could be denoising the input as well as the output values. So what you can do is that instead of taking the input value as it is, you add some noise in that. Okay, and same thing can be done in the output value also. Now with noise, the algorithm can never drive the error to 0. Okay, and then there are other methods like sparse regularization, so that average activation of each neuron is close to 0. So in fact, all these methods, what the algorithm is doing is that it is stopping the algorithm from assuming any arbitrary value that can drive the train error to 0, because in such a case the test error will be high and your model will not be the true depiction of the real life. Okay, one of the key component of the algorithm is activation function, and choice of activation function plays very important role in how good or bad your model is going to be. So there are different types of activation functions. Some of them we saw in the previous sessions. Let us see here. So one of them is, in this example, is known as linear activation function, where each hidden layer is just a linear function of the previous layer, and y can be depicted as weights multiplied by each layer, and these are straight linear function. But in real life, these are not very commonly used. Okay, sigmoid again we saw in the example earlier. What sigmoid function does is that it caps the value between 0 to 1, so you cannot have any arbitrary value of the output. And more importantly, what it does is that it makes the function smooth. Okay, so you see a S-curve here, and the advantage of this is that you will have differentiability at each point. And we know the advantage of differentiability because this is what you use to find out the gradient descent, to find out the minimum value. You have to have a gradient at each point, right? So this is why sigmoid function is used commonly. Now the disadvantage again is that it is not zero centered, so it takes a longer time to converge using this function. And other point obviously we can see is that for a very high value of the input, both on the positive and the negative side, the neuron flattens out, so it has zero gradient. The moment it has zero gradient, you cannot look for convergence, right? So this is another problem with sigmoid function. Okay, another commonly used function is known as tanh functions. It's a tan function. Here again, the advantage is that the output value is capped between -1 to 1, and the function is differentiable at each point, so you always have a gradient. But the disadvantage is that it flattens out again at the higher value, and I think there is a mistake here. So this one is zero centered. Tanh is a zero centered one. Okay, one of the most commonly used activation function is known as rectified linear unit, what is known as ReLU. So as part of this function, up to certain value, up to certain threshold, the output is 0, and beyond that threshold value, it's a linear function. So this function is differentiable if the value is more than 1, more than 0, the value of input is more than 0, and for the value less than 0, this actually flattens out. Now this is computationally very efficient, and this is known to converge the functions much faster than sigmoid and tanh, and it does not saturate because in the previous examples you saw the functions were saturating at the high and the low data points. In this case, it doesn't saturate the higher data side. And disadvantage is the same, that if the value is low, then of course there is no gradient, so it flattens out, and this is what is known as a dead neuron. And if you arrive at that kind of point in your algorithm, then you will not be able to solve it. So to overcome these two problems, there are modified ReLU functions that have been proposed. One of them is called leaky ReLU. So what leaky ReLU does is that it doesn't allow the gradient to become 0 on the negative side, but it maintains a very low gradient, which is like in this particular case is 0.01. Okay, another example is exponential ReLU. So same thing, but in the negative side it goes exponential. Okay, so these were the points that I wanted to cover at a very high level, and these are the techniques you use to improve or fine-tune your model. Again, these are not all, these are not exhaustive, and these are very very illustrative. The idea was just to give you a glimpse of the various components or concepts that are being used in improving the neural network. I hope to see you in the next session. Thank you. Hello everyone, and welcome to this section 4 on deep neural network. In the previous sessions, we spoke about constructing a model, then refining a model. In this particular session, we'll talk about a specific type of neural network known as convolutional network, specially used in image processing. And these are the broad topics that we'll try to cover. Yeah, so in this section, we'll cover the broad concept of image processing and how it is done in deep neural network. There is a concept called convolution, pooling, and then we'll try to construct or we'll try to see different layers in a neural network. The idea is not really to go too much into the detail. At the same time, explain the various components and various constructs of our deep learning. Okay, so let's start with the image processing, and this is a lot governed by how humans see image, right? So an image is different from a typical linear data representation, because in an image, only if you see image as a combination of different pixels, right? Pixels are different values, different color values. Then the way image is processed is the nearby pixels are related, but very far off pixels are not related. So there is a concept of proximity in case of the image processing, which is not the case for, let's say, a normal regression analysis or any data-based network, right? So I have just picked up the example of Taj Mahal. Right, so you can look at this picture as a raw pixel of 20 cross 20, where each cell has some combination of colors. So it could be red, blue, green in a different combination. And that's why if you break these picture into the smallest component, you will have raw pixel. Now, one way to solve this problem is to create a feature map. And that feature map would be a replica of a Taj Mahal, and then you can compare pixel by pixel, and you can say that, yeah, this image is of Taj Mahal. And similarly, you can do it for other images also, like house, car, monument, whatever it is, right? So this is known as static representation of the image, of the features, and there is no learning involved here. So you have a classification image and you have an actual image. You compare the two, find out the difference. If you find a lot of commonality or low error, then you classify that as the right image. But this is not how humans see image, right? We don't do comparison pixel by pixel from our memory or whatever we have, but we only focus on certain features, and these features are important for identifying the image. So for example, when you're looking at face, the important features are eyes, nose, and things like that. The white background behind the face of the person may not be important, may not be significant to characterize that image, right? So this is what is the science behind image processing. It is trying to mimic the way human sees, and in fact our own vision process is very much parallel to that. We see certain things and it goes into our brain, and the bottom or the back part, what is known as okay, let's leave that okay, I'll just drop that part. Okay, okay. So the point that I'm trying to drive is that this has been inspired by the human vision, the way humans see. They identify the most important feature and then they try to characterize the picture based on that. So humans see, our eyes also see the edges, and so one of the component in the image classification is the edge detection, right? So for edge detection, what you do is that you create some filters, and then these filters you can apply on the raw image, and then you can get an image which is far smaller in size. See, the problem with the previous classification was that it was too big. right? So any comparison or any calculation would require huge amount of calculation and computation. So one of the objective of this is of course to find out the important feature. Second is to reduce the size of the input image. So our objective of doing this is to find a hidden representation of an image that is far smaller than size, on which we can do our computations. Okay, as we said, image can be considered as a three-dimensional matrix of pixels, and then these are red, blue, green. They are known as channels. And if we ignore the complexity of the color, we can presume that they're just black and white. In that case, we can think of them as a 2D matrix. Okay, so we spoke earlier that one of the challenge in the image processing is the size of the image, because the pixels are very rich and each cell computations could be very costly. So what we do is part of that is, it is known as convolution. So what convolution does is that it applies a filter on the original image, and it only captures the smaller dimension of that. So I mean, if you have to consider the intuition, filter could be something like the smaller image of the eye or smaller image of the nose, right? So you're comparing a human face and you are matching with those feature list, significant feature list, and then you are classifying it. Okay, so that is the intuition behind that. And what we are doing here is that, let's say this original image of a pixel 01 is there, and then we arrive at this filter. Okay, and then we apply the filter. You slide this filter across the original image, and then you come up with something what is called the convoluted image. So there is no complex calculation here. What it does is that it applies the filter on top of the original image, multiplies each of the input and output, each of the corresponding bits, and then you arrive at the total value. And the filter is slided on the original image, and that is known as stride. So you can, in this particular case, there has been a stride of 3. So you just keep moving your picture. Okay, so this is a mathematical representation. Convoluted image is nothing but a multiplication of the original image and filter being, or the kernel being moved over it. Okay, so convolution, what it does is that it reduces the size of your input image. At the same time, it retains the most significant feature, and these filters are these features. The purpose of pooling layer is to reduce the data size further, right? So this in turn help, same thing, it will help you in easier computations. And pooling layer, what it does is that there are 2 types of pooling. One is called max pooling and another one is called average pooling. Max pooling is used more commonly, and what it does is that it takes out the maximum value. In case of max pooling, it takes out the maximum value of that that particular snap, and then it creates a far smaller image. So if you look at this, the first 4 square boxes, the maximum value is 8, and that's what the pooled image is converted into. And like that, it is the stride is filter is slided through the feature map, and you get this pooled image which is far smaller. Okay, so these are the fundamental principles of image processing, convolution and pooling. And using this, you can create a convolutional network. So convolution network again can consist of multiple layers of convolution and the pooling layer. So in this particular example, there's an input image, and then we create, let's say we take out Here we have taken 6 filters. So using these 6 filters, first layer of convolution is created. Then we can pool them. So all these convolution layer can be corresponded to a pooling layer. Then we can have another layer of convolution on the pool 1 layer. Then again there can be another layer of pooling. So we can have as many number of convolution and pooling as could be applicable for that particular network. And there has been a different kind of image challenges, and different algorithms have used different combinations of the convolution and the pooling. Some cases they have combined the two as well. And then in this particular example, we are trying to create the last layer. There could be multiple layers, as I said. In the final layer, all the outputs are put linearly, and that is known as fully connected layer. And that's what the hidden representation of the, or the shortened or smaller representation of the input image is arrived at. And this is what is used in classification, or it is used in other kind of image processing. So the whole purpose of the convolution is, one, to bring down the size of the image. Second, to find out the most significant representation of the original image, and that could be done as a part of finding out the feature or the filter. Now, in the earlier example, we had given a predefined filter, but as part of the deep learning algorithm, the algorithm also tries to arrive at the filter. So finding out the filter itself is a learning process, and then using these filters we can arrive at the hidden representation of the image. Now, these were the basic principles, some of the very elementary principles of image processing. Now we know that using deep neural network, a machine can have a higher accuracy of image recognition than human, and this has evolved through different phases. And I think this is also one of the most interesting area these days. I hope it will generate some interest in you to study it further. Thank you, and see you in the next session. Hello everyone. Welcome to the 5th session on deep neural network. In the previous session we saw some application in image processing, and this session again will talk about a specific type of neural network known as recurrent neural network. And we'll try to understand why do we need to have this different variety of neural network. We'll try to construct a neural network, and then there is a concept known, especially in case of RNN, or short form of recurrent neural network, is known as short long-term memory. So we'll talk briefly about that. Again, these are very deep topics, and I do not intend to cover all of them or any one of them in depth. The idea is just to give you a glimpse and to give you some intuition behind these network, so that you can explore it of your own. Okay, so first is why a recurrent neural network, why a different type of algorithm is required, right? Now there are different kind of problems that we face in real life. One problem, of course, we saw previously was image recognition, or classifying the image into different category. The other kind of problem that we arrive at is speech recognition, for example, or something that is where the output is not only dependent on the current input, but it is dependent on the context, and where the context becomes important to predict the future outcome. Now, to explain the context let's take an example of reading a story, right? So at any point in time, if you're asked some question about the story, then the way you would answer is not only what happened just at that step, but you would consider everything that has happened in the story so far. So you would consider what are the events that have happened, what are the characters, so all these things are called context. So there are some problems or a lot of problems in our real life where the context becomes very important for any prediction or classification. And our typical model, whatever we have seen so far, they would not be able to solve this because they consider the input, then they apply that algorithm, and then they arrive at the output, right? It does not have any context of what has happened in the last mini cycle. Take the example of stock prices, right? So stock price is just not the function of what is the current price, what was the price yesterday. It is also a function of series of steps that has happened in the past. So all those data points are important for predicting the future stock price. And that's where the recurrent neural network comes into picture. Now, some of the application of RNN is, of course, in next word prediction. This is very heavily used in the natural language processing. And you give them a set of words, and then the network predicts what is going to be the next word. Something that we all know, like when we're typing in a WhatsApp, there is a prediction of the next word, right? So this all comes from the RNN network. And then there are things like image captioning, video captioning, stock market prediction we spoke about, speech recognition, time series. In fact, all the time series are solved using RNN only. Only RNN can solve the time series problem. Also, you can do document classification, like documents are different sentences and there are different paragraphs and all that. So you can do a sentiment analysis, or you can do a finding out of the gist of the document. So all this is required for RNN. Okay. Now, how do you construct a recurrent neural network, right? Now one of the problem with the, in fact, we know that we have been trying to solve a network by finding out the gradient at a particular point and then updating the value of the weights and biases with that gradient. But what happens when the gradient becomes 0, or when you're not able to find the gradient? So in case of recurrent neural network, since the network has a series of you will say steps, the gradient vanishes if you try to backpropagate. The network is too long to backpropagate the error to the original data point, right? So that is the problem mathematically with something like RNN. Okay, so let's try to solve how these RNNs are actually constructed. So let's take an example of auto-completion, and let's say that you have been given 3 words. Man is a social, or 4 words, and you have to predict the 4th word, right? So here, if you just look at, let's say, the word social, you may not be able to predict the word animal. Similarly, if you look at last 2 words, but if you look at the whole sentence, man is a social, then there is a higher chance of predicting the 4th or 5th word, right? Now, there is some characteristic of these types of network. One is like successive inputs are not independent, as we saw that each input has some correlation with the previous input. And the second is like the length of the input is not fixed. Now the sentence could be 4 word, it could be 10 word, or it could be just 3 word or something like that. So this is a very specific type of problem, and that's why we said that we need a different kind of network to solve this, right? So these are the representation of the network. So what it does is, in a normal network, you will have input, you will have a hidden representation or hidden layer, and then you have an output, assuming that there is just one hidden layer. In this case, what the algorithm tries to do is that it captures a state information, okay, and this state information from the previous network is passed on to the next network, and the prediction is done not only based on the current input but also the state information from the previous input. Now as an intuition, this makes sense that it's not just the current word, but the last 3, 4, 5 or n number of words before that should be considered for the prediction of the output. Okay, so this is how the model is constructed mathematically. Here you have one more parameter. So in normal neural network you have weights and biases. Here you have one more parameter to learn, which is dependent on the state of the network, and these are mathematically represented. You can see a state variable which is known as SI, and at each step the state variable will depend on the input variable as well as the output of the previous step. Okay, and the network learns the parameter. Okay, so as we spoke in the previous slide, especially in case of RNN, during backpropagation, there is a problem of vanishing gradient or exploding gradient. Actually, both of them can happen. Okay, at the moment that happens, you will not be able to update your variable. You will not be able to solve or you will not be able to find out the global optima, right? So to solve this mathematical problem, okay, there's a new concept of what we know as long short-term memory, and this again very much works like human memory. And what it does is that it does not carry the entire state information till that point in time. Now, just to draw an analogy, let's say that you're reading a page in the book, okay, and you're somewhere in the middle of the page, right? So what matters for that particular middle of the page line is immediate preceding lines before that image and that line, not the first line of the page or not the first line of the first page, though all of them may have some connection with that, but what matters is your immediate precedence, right? So this is what this concept of memory, and this is how a memory also works, right? So you always capture the immediacy more than the farthest point from the current point, right? So what this LSTM algorithm does is that it does not read all the input that is given to it, and that is known as input gate. Okay, similarly it does not write all the output that it has created. Okay, and then eventually it consciously removes some part of it, that is known as forget gate. So this is a combination of gates, okay, and what these gates do, again, they are mathematical explanation behind each one of them, and then I am covering that at a very high level, but I hope to convey the idea behind it. For example, in the selective write, the previous state information is selectively written to a hidden state, and not the entire information would be contained here. Then input is there, and then after the computation of the output, it does a selective write and then selective forget. So essentially it discounts the values which are far off in the time series, and it considers the immediate value to arrive at the current state and to pass on to the next state. There are various types of LSTM gates, and another very common one is called GRU, gating recurring unit, which is a special case of LSTM that doesn't have any forget gate. So this is a brief about LSTM, and as I said that these are quite deep topics, and I mean, all of them would require a chapter of their own, but as long as you're able to get the idea behind it and why we do it, then we should be, I think it will be helpful. And today, if you use TensorFlow or any of these modern packages, then all these implementations are hidden. I mean, you may not have to specifically code for something like input gate or update gate or something like that. But understanding the idea behind that helps. Thank you and hope to see you in the next lecture. Hello everyone and welcome to this last session on deep learning for beginners. In this session, we'll talk about the word representation and how this is being used, or this is used by all the deep learning model in what we call as natural language processing. And these are the topics that we want to cover here. We'll see first the linear representation of the word, then we'll go to the neural network way, and these are different methods of representation. Okay, so one of the basic way to represent a word is what is known as one-hot representation, and this is very simple, very primitive. Okay, the concept of this is that if there be vocabulary in a dictionary, then there could be a vector of size v, and each word in the dictionary can represent one value of the vector, where one value is 1 and the rest all could be 0. So very simple. Each word as known as one hot. So this is known as one hot representation of the word. So for example, let's say if there are only 4 words in a dictionary, bus, car, dog and cat, then they could be represented by something like this. Okay, where just one of the bit is on and rest all is set as 0. And that's how the entire vocabulary could be represented. So this is very simplistic, but this is a problem, right? So what is the problem? Now the problem is that each word in the dictionary will require a unique representation. It will require a different storage. And assume that if the vocabulary has 10 million words, then you need a vector of 10 million values, right? So basically you need a very complex and lengthy vocabulary metrics to handle this. Okay. Other problem with this kind of representation is that there is no similarity that is captured. So for example, here a dog is similar to cat and a bus is similar to car, right? But if you find out what is known as Euclidean distance between two vectors, all of them have the same difference, right? So all of them will correspond to _√2. So essentially all the words are equidistant from each other, but we know in real life that this is not how the human understanding work, and so this may not be the correct representation of the word, right? Cosine similarity is again mathematical way of representation of similarity between two words, and in this particular case all of them will have 0 cosine similarity. So although this method is very simple, it is not workable in real life due to its size and due to lack of semantics. It doesn't capture the semantics. So then we come to another representation of word. This is known as distributed representation of word. And this was based on a very simple principle, and I mean it's in other form also, but this principle is known as you shall keep a word by the company, you shall know the word by the company it keeps. Okay, so what this means is like you should not only know the word by its meaning, but its relationship with the surrounding words. So for example, if you want to understand the word money, then you'll have to find out the relationship of the word money with other things like bank, credit, capital, and all these words are interrelated. So this was known as distributed concept of word. And the way it is represented is what is known as co-occurrence matrix. So again, this is a very simple representation. Each word in the vocabulary is put in the row, and then each word in the vocabulary is also repeated along the column. And then this matrix tries to find out the occurrence of each of the word within some proximity, within a k window. So for example, if you are trying to find out the co-occurrence of the word bank with money, then you will try to find out in the vocabulary how many places bank and money occurred within the window of, let's say, 2 words or 3 words, right? So these occurrences are captured here, and they are represented in this particular fashion. Now, this is a very simple interpretation. It means that if the words are co-occurring, then they are somehow related. If the words are not co-occurring, then they are not correlated with each other. So that was the principle behind the creation of this co-occurrence matrix. Now this also has some problem. One of the problem could be the things like stop word, right? So you will have word of the repeated so many times, and it will have, so this will actually skew the matrix, and you will not be able to study it properly. And so as a solution of that, either these stop words are omitted or they are capped at some high value. So let's say if the value is more than 100, then you don't capture the co-occurrence anymore. Okay, so to overcome these problems, there is another method that is being used, that is called PMI method, and this uses a specific algorithm. It uses a logarithmic scale of finding out the co-occurrence. Now we can actually we need not go into the details of the formula, but the point here is that let's say if the words are occurring together enough number of times and they are occurring in the dictionary enough number of times individually, then this ratio captures the co-occurrence. And one problem with again this method is that if this if the co-occurrence is 0, then PMI cannot be calculated. So I mean, one of the solution of that is take this PMI value only when the count of or the numerator is more than 0. Okay. The problem with again this distributed processing is the same. It has very high dimension. You have to create all the words in the dictionary, in the vocabulary, and as the size of the vocabulary grows, your basically ability to use this co-occurrence matrix reduces, because the calculations and computations multiply. Okay, so now we come to the modern way of, or maybe I'll say neural network way of predicting the words. So like in all the previous example, they were I mean, the words were being predicted based on either co-occurrence or based on some static value. This one is known as a prediction based model. So in this prediction based model, if you give n-1 word to the network tries to predict the nth word. This is also known as word to vec, and that's where the hidden representation of the word or the neural network comes into picture. So here, for example, if we take an example of let's say Ram sat on and you have to predict the fourth and the fifth word, here in this case chair, right? So here, okay, in the example I have taken the word sat, and then we are trying to predict what is the next word. So this whole representation is done in two parts. One is known as the hidden representation known as the context word, and second is known as the output word, right? The output function is again softmax. So what it does is that it tries to find out the probability of each word in the dictionary given the input word. So let's say given the word as sat, what is the probability of he, what is the probability of man, chair, and things like that, and on in this case. Okay, the network tries to learn the parameters of W word and W context, and loss function is cross entropy at the output layer. Okay, so the difference between this model and the previous model is that here both the W context and W word are learned as part of the algorithm. So this is definitely going to be more robust than the previous model of distributed processing. Okay, and yeah, training method is backpropagation. Another model that is known as skip-gram model. This works something similar, but it has some variability also. So in this particular model, the algorithm tries to predict the context given the word, right? So in case of continuous bag of word, the previous example that we saw, there is only one context word. Okay, but here in this case we are trying to predict both sides of a given word. So for example, if the sentence is sat on a chair and the input is sat, then we are trying to find out the probability of the word before this and probability of the word after this. Okay, and so these are the algorithms that maybe they can be, you can study them in detail. The point here is that how do we find out if the model that you have created or you have chosen is the correct representation, right? So there are different tests for that. One of them is known as semantic relatedness. Okay, in this method you basically ask a human to find out the relation between two words and compare the same using the model, and if there's if the error is less, then you can say that your model is good. Similarly, it could be done for synonym detection. You can ask the model to predict a synonym or pick the right synonym of a given word. And the third one is analogy. All of us have seen that as part of the various reasoning test or something. So something like mother is to father is grandfather is to something. So find out the fourth word. So these are the tests that can be used to find out how robust your model is. Okay, as we know, the previous model is also known as word2vec. Okay, now what is the advantage of using this model? So one of the fundamental challenge with language, when we try to project that in the computer, is the lack of the quantification. So for example, computers understand the numerical data, you can do calculations on top of it, and you can do all those arithmetic operations. But languages do not allow any arithmetic operation in the normal way, right? So the objective of the model should be to convert the language in a form, or what we know as a vectorial form, using which the arithmetical operations can be performed. And by what we mean by arithmetical operation is the similarity between two words, the antonyms, synonyms. So all these relationship can be captured between the word, right? So here, for example, let's say apples is related to apple in the same way as men are related to men. So both are the plural form, right? So this is where the model tries to find out the distance between two words and find out some sense, and you can call it a semantics or something like that. Okay, now this can be extended to anything else, right? So for example, if you could represent each of the word as a vector, then you could do a vector operation on them, right? So for example, let's say through some means, if you could arrive at these vectors for king, boy, queen, or girl, and then if you do some mathematical operation on them, so king minus boy plus girl is equal to, I mean, though it may not make any sense, but if you operate through the vector, then you will arrive at something like queen. So that is the whole purpose of doing this word to vec. You convert language into vector on which you can do mathematical operations. Now, the idea of showing that in 2 dimension was just to give you an intuition. In real life, all these relationships would be hidden representation, and it may not be possible to interpret that. But the point is that it will capture the relationship or essence of the language in the hidden model. That is the concept behind it. Again, I know this is a very brief precursor of the topic, and these are very detailed area of study in natural language processing and other language processing. But the objective was just to give you a brief glimpse and help you understand without any deeper mathematical background. So this was the last lecture, and I hope this course has been useful to you. For any feedback, please feel free to reach out. Thank you very much.